Okay, so let's move on to the multilayer perceptron. So we've shown that single neurons allow us to express very simple relationships, like for example, the implication function, like the different types of Boolean relationships that we observed that we could implement with a single neuron. But obviously, we want to be able to go beyond that. We want to be able to carry out classification and regression tasks. And that's basically going to require to add many more neurons and to organize them into different layers. That's where, multi-layer perceptrons come in. And so what you can see here, this is the typical architecture of a multi-layer perceptron. So each of these circles represent one of the single neurons that we have been studying, right? So any of those has a set of inputs. The inputs are going to be multiplied by weights. So these arrows that you see here are associated to weights. And so you have inputs multiplied by weights. The neuron does sort of processing with the threshold, and then based on that processing, outputs something. However, the main difference is that with a single neuron, you simply had an input layer and then you had an output layer. I mean, you outputted a specific value, right? What you see in the multi-layer perceptron is that we also have a whole bunch of what we call hidden layers. And these layers are not taking a specific input or training data and are also not outputting a specific value that we then check against the target, are just, moving values throughout different layers of neurons. And the idea here behind the multilayer perceptron is that by having these many more neurons and that by having these different layers, we'll be able to better identify patterns in the training data, right? The weights will be updated until we get the desired output or the desired error. And, those weights will try to represent the information that's important, but also the information that is not. So when we train multi-layer perceptrons, again, the idea is that when we run neural network packages that we will see in the examples, basically those packages internally are doing this during training. You will not need to replicate these, but you definitely need to understand so that you can, when you run these packages, you can understand what the different variables are, okay? So make sure you understand this whole process, how single neurons and multi-layer perceptrons are trained. But basically, we're going to assume that the activation function for multi-layer perceptrons that we'll see here is logistic, which is just a type of sigmoid. So again, what's going to happen is that the product of the weights, of the input by the weights, is basically squashed into values between 0 and 1. And now, when we look at this network, it's again exactly the same thing. We need to learn the weights, right? So you basically pass the information through, get the output. Is the output good enough or not? How's the error? If it's not good enough, we need to update weights and thresholds. Okay, it's exactly the same philosophy. And how do we update these weights and these thresholds? So we also apply something like a delta rule, but it's slightly more complicated. Okay, but it's we're differentiating it into like two parts, very similar to what I explained for the single neuron. We have what we call a feed forward. It's basically we pass all the training data through this multi-layer perceptron and we get an output value, okay? And the initial values for the weights for the threshold are basically random, okay? And then we look at the error is not good enough. Then what we do is that we do the back propagation. And what the back propagation means is that we go then from right to left, updating, the weights of the neuron, and then we do another feed forward pass, look at the error, do another back propagation pass, and so on, right? So the idea, it's basically very similar to a single neuron, but in a more complex architecture. We have the input layer. In a feed forward pass, we pass the data through the network, meaning that, the input data is multiplied by the weights. These neurons output certain values that are then multiplied by the weights. These neurons apply, their function and output certain values, and then these values reach the output layer. What the output layer does is that it outputs a specific value, it computes the difference with the target values, and then if the difference is not the difference that we want, is too large, what we do is a back propagation pass. And what the back propagation pass does is that it basically updates all of these weights. When the weights are updated, we do another feed forward. So we pass again all the training data through the network. We look again at the errors. Are the errors good enough? No, they're too high. We do another back propagation. And so basically, this is a loop, like training a neural network is nothing else than a loop with feed forward passes from left to right of the training data and with back propagation passes from right to left, updating the weights of the network. Now, the way the network is trained, as I was saying, it's informed by the training errors, right? So what errors are we getting at the output? For the output nodes, it's crystal clear, right? I mean, you just look at the difference between the target and the actual output value. But for the hidden nodes, it's not. And so the way we compute the error for the hidden nodes is as a weighted average of the error terms of the nodes that use that node as an input, okay? So if you have that node as an input, basically you are taking the weighted average of those error terms. Okay, so I'm going to walk you through a couple of examples for the feed forward and for the backpropagation using two different types of networks so that you familiarize yourself with the specifics of how, multi-layer perceptron is trained when you are using any of the packages that we will be using in R, okay? For the feed forward process, remember that it's just the process that puts your training data through the network in order to compute an output and be able to compare it against the error, okay? So how do we put training data through the network? If we have, sort of these two layers here with neurons 3, 4, and then the output layer with a neuron 5, and we have input 1 and 2, we are calling the inputs A1 and A2. We basically multiply A1 by this weight, and it's an input to 3, multiply A1 by this weight, and it's an input to 4, and the same thing for the second input. So what you have here is that the way we compute A5, if you look internally here, we are multiplying A1 by its weight and A2 by its weight, okay? And this is basically the input to 4, and then 4 applies the activation function. Then what happens with the output from 4? The output from 4 is multiplied by this weight. So we multiply by this weight, right? And this is one of the inputs to 5. We do the same thing with neuron 3. So neuron 3 receives A2 multiplied by the weight, A1 multiplied by the weight, and then applies the activation function. And the output of A3 is multiplied by this weight, okay, which is this part here. And this one and this one, these outputs from 3 and 4, go to neuron 5, and neuron 5 applies the activation function. Okay, so we can rewrite this as weight 3, 5 by the output of 3, plus 4, 5, weight 4, 5, plus the output of 4. And this is a feed-forward pass. So this is basically, the output from neuron 5. This is, our y, the value that we are predicting. And now, obviously, we compare that value against the target value, the value that we are willing to achieve, and that would be the error. So the difference between the label and this value that the neuron has computed is the error. But what the feed-forward process does is just, passing all this information through the network and kind of look at the error. Okay. So now this is an example for the backpropagation, which is also called reverse pass. And here, basically, the backpropagation has multiple steps. I've selected, in this case, the example is going to be with a network that has this hidden layer with the neurons A, B, and C, and has an output layer with the neurons alpha and beta. And so what is the first step for backpropagation? So the first thing that we need to do is to compute the errors, right? I mean, here we've already done the feed forward, and we have computed the output value for alpha and the output value for beta. And so what we're doing here is computing the errors. The error, as we have discussed for the single neuron, is not just the difference between the target value and the actual value from the neuron, but it's actually multiplied by this output value multiplied by 1 minus the output value. Remember that this is just coming from the derivative of the sigmoid function, okay? And so when we compute errors, we use a gradient descent approach, derivative equals to 0, and because we're using a sigmoid, this is, the added element that we need to add to the formula to be able to compute the error when a sigmoid function is used as an activation function instead of a threshold. And so, these are the errors for the two output neurons that we have. Let's assume that, these errors are too high, are not below our desired threshold. So the next thing that we need to do is backpropagate, right? So we're going to be updating all the weights that you see here with the information from the errors that we are getting. And so the first thing that we do is change the weights for the output layer, right? These are the output layer neurons that have these weights associated, A alpha, B alpha, C alpha, and A beta, B beta, and C beta. And so, this is how we update these values. For A alpha, as you can see here, what we do for any single weight, as you can see, we update the weights by using the prior weight, and then the modification is based on the error associated to that neuron as well as on the actual output from the prior neuron, okay? In this case, out A. So what we are doing here basically is saying that this weight here, WA alpha, is going to be modified based on the prior value that it had, but also taking into account the output value of this neuron A that goes to alpha, okay, and the error associated to that output. So, the neuron A, when we were doing the feed-forward process, this has a value that was passed on to alpha, okay, and because of that generated an error, delta alpha, okay, and so we are using that error delta alpha that this value generated together with the output of that neuron to update that weight. And we do exactly the same thing for all of the weights. This parameter nu that you see here is the learning rate, so it's a way of controlling how much importance we give to, the errors from the alpha neuron and, to the output from A. But this is basically how, the weights are modified. In this case, the weights are modified exactly based, on the output from the prior neuron that affected that error and on the error that output partially, caused. The third step, which is the actual backpropagation, it's basically computing the error for the hidden neurons, right? And we need to compute the error for the hidden neurons to then be able to update these weights here for the hidden layer. And so the way we compute the errors here, as you can see in this formula, this is basically, let's take, for example, for the neuron A, the way we compute the error for neuron A is inheriting the errors from the prior neuron that they are connected to, as we were explaining before. And so we take the error for alpha, weighted by the weight that connects the neuron A with the neuron alpha. And because A is also connected to beta, we also take the error from beta and multiply it by the weight A beta, okay? And this is the error that we associate to A. The error is just we are backpropagating the error, from alpha and beta to A. This is exactly what you see here, okay? Backpropagating the error from alpha, backpropagating the error from beta, and again we have this value here. This is just coming from the fact that we are using a sigmoid, and so to minimize the errors we also need to multiply basically by these output values, which in this case are the output values of A, what the neuron is outputting and pushing through these connections. The same thing applies to neuron B and to neuron C. And then once we have calculated these errors, we are in a good position to actually update the weights for the hidden layer. If we look, for example, again at one example, so for example, W lambda A, right, which is this weight here, the way this weight is updated is by considering its prior value, okay, and the error associated to A, and of course the input to lambda. Okay, so what we are saying here is that this specific weight here, it's going to be updated taking into account its prior value, and then we're modifying it by the product of the input value to lambda and the error associated to D. Okay, so again we are just backpropagating errors and saying this is how much the weights need to change to compensate for the errors that we are observing in the output layer. Okay, and this is again the learning rate. And so this is how the backpropagation works. We compute the output errors, we see that they are not small enough, and then we go back. We go back changing the weights in the output and in the hidden layers, and also computing the errors, backpropagating the errors, so that we can, change the weights in subsequent layers. I've prepared this exercise for you. This is a very simple network. okay, where you have these 3 neurons. And so you have these inputs together with the weights, okay? 0, 1, 0, 8, 0, 4, and 0, 6 are the input weights to these neurons, and these are the input values. And what I'm asking you to do is to do a forward pass, so basically put those values through the network and compute the output. And then I'm asking you to do a reverse parse or a back propagation pass, where we basically recompute, weights and errors once, okay? And so the solution is here as well, but I would recommend that, you try to do it on your own before checking the solution, because if you know how to do this, then you fully know how to implement the feed-forward pass and the back propagation in a multi-layer perceptron. And then you'll be able to do to code your own package in R to train a neural network. So, I encourage you to look at this and try to replicate feed-forward and back propagation passes. Now let me finalize the multi-layer perceptron section by talking a little bit about deep learning. Deep learning is nothing else that multi-layer perceptrons that have a lot of layers with a lot of nodes or neurons per layer, and that also have been designed in a way that changes sometimes the way the nodes are connected, sometimes the way the layers are connected, or how the input is manipulated, right? But when you hear about deep learning, sort of the fundamental box, within a deep learning network is just a neuron, a single neuron, like the ones that we have seen. You have probably heard a lot of deep learning architectures. We are not going to cover them in this course. Again, the important thing is you understand neural networks. Once you understand neural networks, sort of understanding more complex architectures is just a matter of seeing how the neurons are used. But there's different types. You might have heard about convolutional neural networks, and these are a specific type of deep learning architectures that basically connect nodes in, like, not all nodes are fully connected. Like all the examples that we have seen, whenever you have a neuron, they have input from different places. So for example, let's look, at this example, right? So whenever you have a neuron, you have basically connections from every single layer, right? And like all neurons are collected to all of the other networks. What convolutional neural networks do is that basically the neurons are not fully connected among themselves, and it's based on neighborhood. So a given neuron will be connected only to other neurons that are in their neighbor, that are nearby. And this is a method that's generally used, have been successfully used to do image processing. You might also have heard about recurrent neural networks, and a subtype of them, long short-term memory networks, or LSTMs. Recurrent neural networks are basically, their main characteristic, besides having a lot of layers, a lot of nodes, is that basically a neuron can have a connection to itself. That's why they are called recurrent. So, for the simple models that we've seen, the arrows always connect different neurons. So you would have an arrow to itself in a recurrent neural network. Long short-term memory neural networks are basically a specialization and improvement of RNNs, in that they also have the ability, these are models that have the ability to identify long-term patterns, like, certain information is not forgotten when it exists, when these patterns exists in the long term. And then, of course, you might have also heard about transformers. Transformers, which are sort of the technology behind all the generative models that we are hearing about, right? And so what transformers do, their main distinction, or what set them apart and made them more successful, was what it's known as the self-attention mechanism. And basically this is just a way of amplifying or diminishing the importance of different elements in the input data. So in a way, it's, selecting the things that are useful and ignoring the things that are not. And transformers are really good at doing that. And transformers were actually, as I was saying before, the deep learning architectures that have led to the development of generative pre-trained transformers, or what we all know as GPT. And, based on those GPT models, applications like ChatGPT have been created. And talking about applications, so, I've already mentioned ChatGPT, but, there's, for example, IBM's Jeopardy, that won the IBM Challenge, basically. And this is a question answering system, and, it's based on deep learning. Facebook's face recognition also uses deep learning. Skype's real-time translation also uses deep learning for machine translation. ChatGPT and so on are just some examples of deep learning architectures. Again, in this course, we are not covering anything else about deep learning, so just make sure that you understand how very simple neural networks works, because that's sort of the building blocks for when you want to work with more complex deep learning architectures.